Hey, welcome back to The Explainer. Today we're diving into the physics of spin. You know, it's kind of wild when you think about it. A rolling ball, our own planet, a figure skater doing a pirouette, they all play by the exact same incredible rules of rotational motion. And today we are going to break down exactly how that works. All right, let's jump right in with a little challenge, a mystery that really gets to the heart of what we're talking about today. It seems like a simple race, but trust me, the winner reveals a deep, deep truth about the physics of spin. So here's the setup. Picture this. You've got a solid ball and a solid cylinder. Let's say they have the exact same mass, same radius. We put them at the top of a ramp, side by side, and we let them go. Who wins? Who gets to the bottom first? The ball, the cylinder, or is it a dead heat? Go ahead, make a guess. Lock it in your head. We're going to find out. Now, to solve our little mystery, we first need to get the language down. We have to learn how physicists actually talk about things that are spinning. It's a whole new way of looking at motion. Okay, so first things first, forget about degrees. Just for a minute. In physics, the real natural unit for angles is the radian. And it's actually a pretty simple idea. A radian is just the angle you get when the slice of the circle you're looking at has an edge length that's exactly equal to its radius. One full spin, one revolution, is just 2 pi radians. It's the language of rotation. And what's so cool about this is that for pretty much everything you know about motion in a straight line, there's a perfect rotational twin. So instead of how far you've gone, displacement x, we have how much you've turned, angular displacement, theta. And instead of how fast you're going, velocity v, we have how fast you're spinning, angular velocity omega. See? It's like a parallel universe for physics. All right, let's grab our next clue. What makes something start spinning anyway? I mean, for linear motion, it's a force, right? A push or a pull. But for rotation, it's a little more clever. It's something called torque. Think about opening a heavy door. You know this intuitively. If you try to push it open right next to the hinges, nothing happens. It's incredibly hard. But if you push on the opposite side, out by the doorknob, it swings open easily, even with the same push. That difference, that's torque in action. So if you really want to get something spinning efficiently, how do you maximize your effort? It boils down to 2 key things. First, push as far away from the pivot point, the hinge, as you can. That distance is your lever arm. And second, push straight on, perpendicular to the surface. Don't push at a weird angle. Do those 2 things and you're getting maximum twist. And here's the official definition. Torque, which we write with the Greek letter tau, is basically the rotational version of force. You just calculate it by multiplying the force you apply by that all-important lever arm. More force, or a longer lever arm, that means more torque. And more torque means a bigger change in how something is spinning. Okay, let's get to our last and honestly most important clue for our race. This is the rotational version of mass. It's called rotational inertia, and it's all about how much an object resists being spun. Right, so you know mass is about how hard it is to push something in a straight line. Well, rotational inertia, we call it I, tells you how hard it is to start something spinning or to stop it once it's going. And here's the absolute key. It's not just about how much an object weighs. It's about where that weight is. The shape is everything. This is the perfect way to picture it. Take a hollow hoop and a solid cylinder that have the exact same mass and radius. For the hoop, all its mass is way out on the edge, far from the center. For the cylinder, that mass is spread all the way through. Because the hoop's mass is further away, it has a way bigger rotational inertia. It's just harder to get spinning. Now let's look at the actual formulas for our racers. Don't worry about the mr² part, they're the same for both. Just look at the fraction out front. For the cylinder, it's 1/2, or 0.5. For the sphere, it's 2/5, which is 0.4. See that? The sphere's number is smaller. That tells you, for the same mass and radius, the sphere has less rotational inertia. It is fundamentally easier to get a sphere spinning. Okay, we did it. We've collected all the pieces of the puzzle. We know about torque, and crucially, we understand rotational inertia and how shape matters. So, it's time. Let's go back to that ramp and finally declare a winner. So at the top of the ramp, both of our objects have a stored-up tank of what's called potential energy. It's the energy of height. When we let them go, they have to spend that energy on motion, on kinetic energy. But here's the trick. For a rolling object, that energy has to be split. Some of it goes into moving forward down the ramp, we call that translational energy, and some of it has to be used for spinning. That's rotational energy.
And here it is, the big reveal. Both objects start with the same energy budget. The one that is easier to spin, the one with the lower rotational inertia, has to spend less of its precious energy on just the act of rotating. You could almost say it wastes less energy on spinning, and that leaves more energy in the budget to spend on what wins the race, moving forward.
And we already saw the numbers, right? The ball's factor is smaller. It requires less energy to get it spinning compared to the cylinder. It's just a more efficient shape for rolling. So the ball gets there first, every single time. Because it wastes less energy getting itself to rotate, it can put more of its initial energy into pure straight line speed. It doesn't matter what they're made of, how heavy they are. If you race a solid sphere against a solid cylinder, the sphere always wins. Okay, now that we've cracked that puzzle, let's look at maybe the most elegant and famous example of these principles in the real world, the spinning figure skater. It's absolutely beautiful to watch, and it's pure physics. So when a skater starts a spin, they often have their arms held out wide. Just like our hollow hoop, this puts their mass far away from their center of rotation. This gives them a really high rotational inertia, and for a given push-off, their spin is relatively slow and controlled. But then, watch what happens. They pull their arms in tight to their body. By doing that, they are bringing all that mass closer to the axis of rotation, which dramatically lowers their rotational inertia. And to obey the laws of physics, their spin speed has to shoot up to compensate, and suddenly they're a blur. It's incredible. What's going on here isn't magic. It's governed by one of the most fundamental laws of the universe, the conservation of angular momentum. It just says that for anything spinning, its rotational inertia, I, times its angular speed, omega, has to stay constant, unless some outside twist acts on it. So if I goes down, omega has to go up. It's the law. And that brings us to one last pretty mind-blowing thought. The Earth is a spinning object too. So what do you think happens if the polar ice caps melt and all that mass, all that water, moves from the poles, our planet's axis of rotation, and spreads out towards the equator? It's just like the skater extending her arms out, but on a planetary scale. Would that actually change the length of our day? It's the same physics. Something to chew on. Thanks for joining us on The Explainer.